Good day, everyone, and thanks for joining our webinar on Synergizing Solutions, Process Intensification for Municipal Wastewater Challenges, presented by Veolia Water Technologies. My name is Ted Ralsey. I'm the editor of Treatment Plant Operator magazine, and I'm the moderator for this session. To meet the challenge of growth and stringent permit limits while also eliminating discharges caused by wet weather events and infrastructure development, Veolia has combined the benefits of two leading treatment technologies. The ZWeed membrane bioreactor provides enhanced nutrient removal, while a biologically enhanced high-rate ballasted clarification technology called BioActiveFlow provides secondary level treatment of wet weather flows. This presentation will show how the combination of these two technologies delivers significant savings in overall project and operating costs, while providing a resilient and proven solution for municipalities. The presentation will include case studies of existing full-scale installations. For those who may not be familiar, Veolia Water Technologies is a world-leading specialist in water, wastewater, and biosolids treatment equipment for industrial and municipal applications. Its expertise is focused on preserving the environment, helping customers reduce their carbon footprint, optimizing water consumption, and maximizing energy resources as part of their ecological transformation initiative. Before we begin, you'll notice on the right side of your screen a drop-down menu titled Questions. You can use this function to submit questions to our presenters, and you can do this at any time during the program. We'll leave time at the end for our presenters to answer questions we've received. With that, let's begin. We have two presenters today. Reed Staten is the product development manager who supports Veolia's ActiveFlow ballasted clarification system. Based in Cary, North Carolina, he has a degree in mechanical engineering from North Carolina State University and has been with Veolia for 22 years. He's also been a mechanical and process engineer and a process manager with Veolia. He has extensive experience in process engineering and the operation of physical, chemical separation, and filtration processes in water and wastewater treatment. Jason Kaiser is Veolia's regional sales manager for municipal systems in California and Arizona. He has over 2 decades of experience focused on the application of membrane treatment systems for municipal and industrial applications. With the limited water resources in the southwestern United States, the use of MBR is becoming the norm, and therefore Jason works with customers on MBR projects daily. With that, I'll turn the program over to our presenters.
Thanks, Ted. Good afternoon, everybody. This is Jason Kaiser. So today we're going to, as Ted introduced, we're going to talk about two technologies that typically you don't see married together. With that, though, as technology develops and as adoption of technology grows, we've taken these two technologies and shown avenues where you can couple them together to solve multiple problems at once. So today we're going to go over a few key points here. We're going to look at the trends and challenges, the specifics around the two technologies, some case studies, and closing thoughts which show the pros and cons of the melding of the two technologies. So as we at Veolia talk to our customers, there are common themes amongst the needs of our customers, but there are regional shifts, and those regional shifts do stress some things over another. As such, unfortunately, there's no one-size-fits-all solution. So we look at it from a perspective of what can we do, how can we modify our offerings to best suit our customers' needs, at the same time allow those offerings to be flexible enough so that they can adapt to various conditions. As populations grown, as population shifts, the needs of each individual do fall within a range, but they those needs do shift over time. So an example would be as population shifts or grows in a particular area, how can I get more work out of my existing infrastructure? What can I do to modify said process or expand my facility? At the same time, if I simply can't get more out of my facility, what can I do to build a new facility? So a greenfield expansion. As I do that, I need to plan for the future. At the same time, nutrient requirements and effluent quality and the need to do something else with that water does change as well. So if we look at the Southwest United States, there are a couple of major drivers there to push the effluent quality to be better. Not because it needs to be discharging the environment, we have to protect the environment, although that is certainly the case, but can we take that water a step further and reuse that water in a meaningful way? Lastly, this one item does fall on every customer's mind is what's the resilience, the process resilience, the equipment resiliency. I need to be able to trust this solution day in and day out. Reed?
Thanks, Jason. As Ted mentioned, Reed Staten with Veolia here as well, along with Jason. But as we transition from one set of challenges, another set of challenges that many municipalities face is wet weather. And managing the impact of wet weather is one of the most costly challenges that many municipalities face. And there's a variety of factors that play into that. And at the top of that list is aging infrastructure, and that starts with collection systems. There are over 1 billion miles of collection systems here in the U.S. alone, and they all have their own unique complexity and different sets of challenges. And it's one major hurdle that utilities have to overcome. Urbanization and impervious surfaces, the increase of growth, especially in bigger cities, contribute to that as well, increasing stormwater, increasing the amount of impurities that this stormwater picks up. And of course, all that works its way in some shape or form back to the plant. And a lot of plants are undersized. They're reaching their age of life as well. They have treatment challenges, especially at peak flows, but many of them have pinch points from a hydraulic perspective all throughout the plant. So all of this, are contributing factors to what municipalities have to manage and ultimately lead to the thing they're trying to avoid, right? Overflows in the network or bypassing flows around their plant, which ultimately pollute waterways. They contaminate our drinking water sources and ultimately lead to public health, environmental, and economic impacts. And when any utility or municipality is looking for solutions to overcome these challenges, kind of like Jason said, at the top of the list is flexibility and resiliency for a solution to be able to adapt and be capable of withstanding the dynamic challenges of wet weather. It's very unpredictable, and having solutions in place to manage that is important. And then, of course, as weather occurs, as ground saturation increases, as inflow and infiltration starts to increase flow to plants, operators have their hands full. Manpower is tough right now, and the last thing a plant needs is something that's more complicated to operate, that requires more maintenance, that doesn't meet performance. And so, in having reliability and simplicity is also important in the overall picture. Next slide, Jason. So from Veolia's perspective, we have a wide range of solutions, but what we'll talk about at length today are two key solutions, as Jason alluded to, that offer some synergies when combined together, that work well together, that have similar advantages and similar process resources that allow those two to come together in a unique way to help solve a lot of these challenges that we talked about. And it'll start first with membrane bioreactors, an activated sludge bioreactor with submerged membranes that Jason will talk at length about. And then from a wet weather perspective, we talk about bioact flow We talk about active flow and high rate, and we'll talk some about the differences of that. But again, it pairs contact stabilization with the enhanced high efficiency clarification of active flow. And again, both of these combined, help municipalities essentially do more with less. Next slide, Jason.
Thanks, Reed. So first, we're going to go ahead and talk about membrane bioreactors and specifically the Veolia solution there. Membrane bioreactors are, if we rewind the clock 20 years ago, were not as commonplace. They were up and coming then. They were always deemed as the expensive option. Oh God, if I have a water quality event, this protects me, but I'm really going to pay for it. If we fast forward to today, that's not the case. MBR systems have become very commonplace, and the cost, when you look at the total installed cost of an MBR versus an activated sludge plant, followed by secondary clarification, followed by some sort of tertiary filtration. If you look at those, the MBR system generally floats to the top as being the best option, addressing all the needs of a customer while being a lower cost option. That said, MBRs do present some operational nuances to them that any owner needs to be aware of. First of all, I have a system that inherently uses pumps and blowers, and so I have more equipment perhaps to maintain. Second of all, that equipment uses electricity. And third of all, what happens to my system when the flows into my system change? And so that's what we're talking about today. So, all the nuances of MBR can be distilled down into a couple of key points and why somebody selects an MBR. First of all, it's a high rate, intense process. So the process intensification checkbox is already checked with MBR because you're using a higher mixed liquor concentration, which then results in a biological treatment process that's very compact, followed by a liquid solid separation step, again, which is very compact. And it turns out an effluent quality that is consistent day in and day out. Consistently we get solids-free water, low nitrogens and phosphorates, and a water that is already prepared for some sort of beneficial reuse, whether that be irrigation purposes or potable reuse. The water is well positioned, already prepped for those processes. MBR systems as a whole have also become very reliable. The process is consistent. It runs day in and day out, and membrane manufacturers have demonstrated that their product lasts a significant amount of time, thus reducing the previous advertised operating costs. If we look at the membrane life, in the case of Veolia's offering, we're exceeding 15 years of membrane life, which is unfortunately not what we advertised to the marketplace years ago. It was generally expected to be about half of that. So when we look at doubling the membrane life in the last number of years, it has a profound impact on your total cost of operations. As previously mentioned, MBR is the epitome of a compact footprint. You're conservatively reducing your footprint size by 50% over alternative unit processes. And lastly, if you look at that compact footprint, the amount of concrete and steel and labor that has to be invested in construction of a facility, MBR always comes in as a low-cost option when you look at that constructed cost. So what's the negative here to an MBR system? Well, as one could expect it, as there's flow variances into a system, those have to be addressed. And MBR can address those. The issue becomes as the peak factor exceeds a factor of 2 off of your average, that peaking factor becomes the determinant point in the design of the membrane system. As such, to treat flows that are generally in excess of 2 times your average, you have to install more membrane area. In doing so, you now have more membrane area to purchase and care for. The footprint at your facility starts to grow. So the high rate process that it once was is still high rate, but you're designing and installing and constructing facilities that are larger than they need to be on average because of this peak flow. Going hand in hand with that, equipment needs to get larger or more equipment needs to get installed. And so the maintenance on said equipment, your valves, your rebuilds on your valves, your sensors, the number of items that are needing care goes up. Lastly, power and chemicals can change as well. Generally, as you design for larger peak flows, the basins get larger, and as a result, the chemical consumption goes up. Power can go up as well because you have to operate said equipment. So you have pumps that are larger, blowers that are larger. It's generally to a lesser degree, but it is a factor that needs to be considered. So as we look at the total installed cost and a life cycle cost of operating a MBR facility over a lengthy period of time, say 20 or more years, we've seen how if you can shave those peak flows off in some way, it has a beneficial effect to the overall life cycle analysis. So if we look at that and we couple it to other technologies, what technologies fit that bill? What technologies are easy to operate? What technologies are available in the marketplace that help me run my MBR system at its optimal year in and year out?
And that's as we transition to bioactive flow here, as Jason alluded to, the benefits of MBR and being able to handle a variety of conditions. But when we reach those situations where larger flows are needed, especially under peak wet weather events, is there a synergy here with other technologies? And bioactive flow fits that bill with respect to experience in the wet weather industry. And we'll talk more about bioactive flow, but I just want to take a step back from Veolia's perspective. When we talk about wet weather treatment, we have over 20 years of operating experience here in the U.S. alone, plants all across the country. And from a bioactive flow perspective, over 10 years of operating experience. And for those not familiar, next slide, Jason, what is bioactive flow? So bioactive flow combines essentially two proven technologies, contact stabilization with high rate clarification, or what here at Veolia we call active flow. For those not familiar with active flow, it takes your standard coagulation, flocculation principles for coagulating, flocculating, and enhances that with a ballast. And what that ballast allows us to do is to take a very slow settling velocity and dramatically increase it by attaching that ballast or that anchor, so to speak, and dramatically decreasing the residence time through the process, but also dramatically increasing the service loading rate or gallons per minute per square foot of area, which leans in towards the ease of constructability, the savings costs associated with that. So taking the advantages of active flow and combining it with that contact stabilization basin upstream allows us to target the soluble BOD fraction coming in with the wet weather influent flow. That's going to be absorbed onto the mixed liquor. That mixed liquor will carry into the clarification step, will capture that TSS, and in turn, not only meet secondary standards for TSS through bioactive flow, but also meet secondary standards with respect to total BOD removal as well. Next slide, Jason. And so if we look at just in a graphical form here, we talked about active flow. It's kind of the building block of bioactive flow. There's lots of experience with active flow in a wet weather application. Active flow can be installed in parallel treatment, just like this is shown, where it treats those peak flows that are bypassed around the hydraulic pinch points, typically the biological process, or clarifiers, treating it for suspended solids removal before blending that back into disinfection. Active flow can be in parallel treatment or also located out in the collection system as a satellite facility as well. But if we switch to bio, Jason, next slide. Again, we're building upon the adaptation of the clarification step, the high efficiency clarification step. But in this case, we're taking that bypass flow around the biological step, and we're going to borrow a little bit of RAS and take advantage of that excess biological activity within the contact tank, allowing that mixed liquor suspended solids of anywhere from 500 to 1200 milligrams per liter, depending on the SRT and what we're trying to achieve, allowing that mixed liquor to absorb the soluble BOD onto the mixed liquor, and then that moves into the high efficiency clarification step of active flow. We'll remove those suspended solids, which also allows us to meet total BOD as well before that's blended back in for disinfection. Again, RAS is obviously important from the main plant perspective. I mentioned we're only borrowing it, so as we pull off that RAS stream and it moves through the process, we will continuously recycle that back to the NBR biological process for reuse and reoxidation. And it's important to note here too that bioactive flow and active flow, right, have unlimited treatment capacity, right? So no matter if it's a 1 hour event or a 3-day event, but active flow and bioactive flow can provide continuous treatment throughout the entire duration. Next slide, Jason. Just a quick summation of performance anticipated through both active flow and bioactive flow. As you can see, with the clarification step, very efficient removal of suspended solids, obviously with the coagulation and precipitation of ortho, phosphorus. We can also capture high levels or meet really ultra low levels of phosphorus through both of these systems. And then of course the effluent is easily disinfected and has high UV transmittance. BOD is really what separates these two technologies. Again, the particulate fraction is easily captured through the clarification step, but it's that contact, it's the pairing of clarification with that contact stabilization zone that allows us to target the soluble fraction, absorbing it onto the next liquor, and then clarifying that to achieve secondary standards with respect to both TSS as well as total BOD. Next slide, Jason. I talked a little bit about the experience. Just wanted to highlight the installations for both active flow and bioactive flow, over 30 wet weather installations here in just the US alone. The blue reference points here are your active flow references in either a CSO or an SSO application. And then your purple reference points here are your bioactive flows. And to date, we have 8 total installations. And of all 30 installations, we have installations ranging from a few million gallons a day of treatment capacity to our largest at 250 million gallons of treated capacity. Next slide, Jason.
Okay, so our first example this afternoon is the Cox Creeks Water Reclamation Facility in Maryland. The facility is something we see very common in this area. Discharge into the Chesapeake Bay tributary has some very stringent requirements for nutrients, both in nitrogen and phosphorus, because as expected, the impact to the environment when we're discharging excessive limits of either is profound. Additionally, it's a high density area, so spatial congestion is there, and one of the things that is one of the major drivers to push them to an NBR solution. Now, if as you read this slide, if you remember what I said a few moments ago, if we can keep our average flows to our peak flows to a ratio of 2, generally that's something that can be handled by the MBR without any special consideration or motivation. In this particular case here, you see we're at a factor of 3. So what if you consider that coupled with the diurnal flow swings, which are 40 to 150% of norm, it does present a little bit of a challenge on how can I best spend my money as an owner, meet my water quality, and handle the range of flows that I get. So Cox Creek is a fantastic example of what we're talking about here today.
Exactly, and as Jason alluded to, that peaking factor is really what the engineer and the owner started looking at with respect to, as Jason said, how can I make the most of the dollars that I'm spending? And so an evaluation took place to not only look at the MBR side in terms of what can be done there, but also are there alternative solutions like Jason alluded to. And so BioActFlow, we worked with the engineer to look at a life cycle evaluation. And what the engineer ultimately arrived at is, with the installation of BioActFlow, not only can we help shave off that peak flow, more optimize the MBR offering, but it also helps, like Jason talked about earlier, it helps benefit not only a capital cost perspective, it helps reduce footprint, it helps reduce OpEx while not sacrificing the effluent quality and the ability to biologically treat all flows and have a peak wet weather capacity through the plant. So BioActFlow was chosen as part of this, just like MBR, to, again, a synergy effect, really find the best balance across all aspects of the project with respect to overall cost, overall construction, and overall OpEx, while still meeting a high level of effluent quality through the MBR, but also the BioActFlow during wet weather treatment. And again, you can see, as we alluded to earlier, some of the anticipations of performance that were guaranteed on this with respect to BioActFlow. Next slide, Jason. So the next case study we want to highlight is on the opposite side, out in California, San Mateo. As plants evaluate all their challenges that we talked about earlier, right? They look at everything, that can be done to a given facility. What are my challenges? How can I solve it? And they go through essentially a facility plan and figure out how best to solve those challenges. And just wanted to highlight a few things that San Mateo went through, and to give some background on some of their challenges. Aging infrastructure, like we talked about earlier, not only on a wastewater treatment perspective, but they also have challenges in the collection system in terms of aging infrastructure. Their wastewater treatment facility is not only old, it's reaching its end of life. There are a number of hydraulic challenges throughout the plant, secondary capacity, outfall capacity limitations, and you can see the projected flow there that Corolla projected out back in 2014 of 98 MGD. So you have a hydraulic, how do I handle this and how do I ensure that I've got my peak weather capacity? But they also took a close look at their collection systems, and over 230 miles of complex, diverse collection systems that have a number of weak points. We talk about short pipe segments and all the joints associated with it, and they had a lot of infiltration and inflow associated with those joints. They had undersized pump stations. So just a number of challenges that I'm sure many municipalities face. And so the city of San Mateo sat down with their consultants and put this facility plan together with the intent of saying, all right, how do I increase my wet weather capacity? How do I eliminate my overflows and my blending scenarios? And then ultimately, because of where they're discharging and focus on reuse, how can I meet more stringent effluent quality? Jason, next slide. And so when you look at the overall picture, and most every solution, when we look at a wet weather challenge and what most municipalities do is they tackle many areas of concern. And San Mateo started with their collection system. A lot of their collection systems were in right-of-ways, hard to access. So they focused where they could in improving those and put a lot of their energy and effort into pump station upgrades. Storage was also an option. They had on-site storage that they could retrofit and rehabilitate. They also implemented out in the collection system some additional storage that helped shave off some of those peak flows. And then as part of a technology and a process evaluation, MBR was considered along with other biological components and technologies, but also how do I treat the wet weather? And so bioactflow, bioset were technologies that were considered as well. And very similar to Cox Creek, the ability to shave off those peak flows with respect to the biological system helped maximize the overall offering with MBR, and that coupled with the compact footprint that Jason talked about really allowed them to fit this within a very tight footprint on site that is very site restricted. And then bioactflow, again, helping with the MBR sizing of things, but also the other technologies they were comparing bioactflow to. Bioactflow was able to recognize a significant amount of savings in terms of overall footprint, but because of where the site was, piles that had to be poured, there was a significant reduction in excavation and hauling volumes as well. This plant is currently under construction. There's actually an existing plant that we talked about. Part of this facility plan was actually to build a greenfield site right next door to the existing plant. Part of the overall facility plan was to make some minor improvements to the existing plant just to keep it online through the construction phase. And as we bring both MBR, bioactflow, and new plant online, they will be phasing the old plant out. Jason, next slide. And then some closing thoughts. As we've talked about today, when you look at both technologies independently, right? They're well established in the market. They provide significant advantages to meet the needs of customers, of consultants, and solve some key problems that everybody faces. MBRs, are resilient, are robust. They provide a high level of treatment to whether it's reuse, whether it's Title 22, and improving the environment. They do that all in a very compact footprint with a high amount of biomass. And that pairs well with bioactflow, which has the experience on a wet weather perspective. The ability to increase a plant's wet weather treatment capacity, provide unlimited capacity, and provide a high efficient removal of suspended solids, but also being able to target that soluble fraction and allow bioactflow in a wet weather treatment capacity for any flows that are diverted, ensuring and giving the plant a level of comfort that they can also meet secondary standards with respect to TSS and BOD during that wet weather. The synergy between these two product lines, between these two technologies, complement each other, and then again working together to provide an overall cost-effective solution for municipalities in the multitude of challenges they face today. Jason, anything else to add before we turn it over to Ted?
All right,
no,
thank you, Reed.
You did a great job. Thanks.
Yeah, thank you, Reed and Jason, for that excellent presentation. And now it's time to answer the questions you've submitted here today. Remember, you can still submit your questions using the function at the right side of your screen. First question we have is, what is used to ballast the MLSS to increase settling times? How does the addition of a ballast material affect sludge production?
So I think this is related to bioactive flow and the ballast we use within the process. So twofold. If we take a step up to the contact stabilization zone, the RAS we pull into the process because of the high DO associated with MBR, we're really not necessarily looking to add additional air. It's really just about keeping that mixed liquor in suspension. We can do that with coarse bubble diffusers. We can do that with surface aerators like we did in Cox Creek. There's just a variety of ways to be able to keep that mixed liquor suspended and interacting with the influent wet weather that's coming into that. And then as that mixed liquor passes through the contact stabilization zone and into the clarification process, right, we'll coagulate, we'll flocculate, and we'll bind that mixed liquor to the ballast within the active flow process, which is essentially silica sand, a very dense, very heavy particle compared to the mixed liquor within the process. And again, that's that anchor that we talk about that affords a very high settling velocity, very compact footprint associated. And as we continuously remove that sludge as it settles within the clarification step, we're going to separate the ballast to ensure it recycles back into the process and that we can use it again, and separate that ballast. And essentially what's left is just the mixed liquor that we settled out. And that mixed liquor, again, because we're borrowing it from the main plant, will just go back to the biological process for reuse and reoxidation. So no impact to, the amount of sludge, what have you, compared to what we're just borrowing from the RAS.
Yeah, and I'll add to that,
how much...
the amount that we're borrowing to, let's say, seed the contact stabilization zone, because MBR has such a higher mixed liquor concentration inherently, and because we're borrowing it from the RAS zone, it's in the upper percentile, or it's at the highest concentration that it's typically at. So the volume that we have to borrow is relatively low to seed the contact stabilization zone. And even if it was a bit more pronounced due to a high amount of flow, the biological process, the amount that we're borrowing from it is rather insignificant, and we don't see upsets to the, let's call it the MBR system's only biological mass. And as Ree said, that mass that we borrowed gets returned back, albeit maybe with a slight increase in solids from the coagulant, but still relatively small in the total amount of mass that we are having to steal.
Okay. So the next question we have is, what was the initial footprint of the system before the 40% reduction?
I think this is in question or in relation to the San Mateo facility, I think. And I don't have numbers off the top of my head, but those are numbers we can absolutely, dig back into and share, at least with respect to bioactive flow. As we talked about, the way the available land that San Mateo had available to them, building, next door to the existing site and the degradation of the existing plant, they didn't have a lot of land to work with. And so the technologies that were at least initially looked at by the time bioactive flow was being considered were much larger, much lower loading rates, and it's those higher loading rates that really afforded bioactive flow a significant savings in terms of overall footprint.
All right, next question. How much return activated sludge is needed when operating bioactive flow?
Yeah, as I alluded to earlier, depending on, the influent conditions, especially the soluble fraction of BOD on what may be present across, all the varying flows a plant may see, and what we're trying to achieve on the effluent side. Mixed liquor concentrations can vary. We have plants operating on the low end of a few 100 milligram per liter. And then for higher soluble fraction waters that are a little more challenging, maybe a little bit more activities needed, we could be upwards of 1,000 to 1,200 milligram per liter of suspended solids that we're maintaining within the process. So if you look at, as Jason alluded to, with the MBR and its higher biomass inventory that it maintains compared to other conventional activated sludge technologies, the amount of RAS needed is minor. If we put numbers to it, during a short event duration, we're probably looking at 12% of forward flow of the amount of RAS needed. And as Jason alluded to, and as we've talked about in the past, as soon as that, it is obviously on a continuous basis pulled, a minor amount pulled from that RAS stream, but on a continuous basis, we're also settling that RAS out and sending it right back to the biological process to avoid any issues during the wet weather event.
All right, next question is, how much time does it take to get BioActiflow up and running?
So obviously wet weather is hard to predict, right? It's dynamic. Ground saturation plays a large role in how much flow potentially could be seen. And so obviously the amount of time a plant has to react can vary. As far as BioActiflow goes, most of the time the tanks are stored dry or wet, so they're already full. Chemical lines are often already charged, ready to go. It's just a matter of, essentially letting what we call one hydraulic residence time happen. And the hydraulic residence time through a bioactive process is on the magnitude of 30 to 40 minutes at most. So, essentially through a PLC automation or some type of level initiation based on upstream conditions, the system can be triggered at start. Equipment will start rotating, the chemical feed will happen. And with, like I said, 30 to 40 minutes, we're able to meet, the secondary standards that we talked about with respect to TSS and total BOD.
All right, next question. How much operational flexibility does BioActiflow have in handling wet weather flows?
So one of the key things with ActiveFlow, and of course, BioActiflow, is the amount of ballast that we maintain within the process. Depending on the situation, we could be anywhere from 3 to 8 grams per liter, and that concentration is significantly greater than anything that we would see with respect to influent conditions or mixed liquor suspended solids concentrations, and that acts as a buffer to really help dampen any variation that is typically seen during wet weather with respect to flow or influent suspended solids concentrations. As I alluded to earlier too, with influent or wet weather events, it's very difficult to predict how long they'll last and when they'll start, and there's really an infinite runtime associated with BioActiflow. There's no limitation on how long you can run the system. Whereas storage or other means, right? At some point, the tank fills and you've got to figure out where else to put the water. So here, as long as you're sending water to it, the system can treat it. And then with wet weather, it's not uncommon to see, especially during the initial surge, influent concentrations of higher concentrations in terms of suspended solids. And then depending on the event, over the duration, those suspended solids often decrease and the water becomes more dilute. And through chemical adjustments, often semi-automated or automated through the controls, chemical demand can adjust throughout the duration based on those suspended solids to try to simplify the overall operation of the system for operators.
All right. It appears that those are all the questions we have. Are there any final points that our presenters would like to leave our audience with?
I just want to thank Jason and Ted and you guys for hosting and for all those that attended. I think our information, both Jason and I, will be shared. Please reach out with any questions. Happy to talk, any additional questions or applications you may have, and see how we can help you to work with these two solutions.
All right. Well, if there are no further questions, then that concludes our program. We hope you've gained insights you can use as you consider nutrient removal and wet weather technologies for your water resource recovery facilities. If you have other questions for our presenters and the team at Veolia Water Technologies, you'll find the instructions in the follow-up email that you'll receive. There will also be sent out a certificate for credit hours for attending this webinar. Thanks for your participation and have a productive day.